Hello everyone. In this video, we are going to see about what is the knapsack problem using a branch and bound technique, how that problem is solved. So already we came to know that the knapsack problem means we can get the maximum profit with the minimum number of value. So in that knapsack problem, using branch and bound is one of the technique is used to problem. So it is a branch and bound is not, it is one of the problem solving technique. Here we are using the birth first approach to solve the problems. It is similar the backtracking and also uses the state space tree. So here we are given a maximum, it is given the produces a maximization problem, but we can convert into the minimization. So what is a knapsack? So in the knapsack problems, we have to, there is a sock. In the sock we have to, they are given the capacity of the sack, and we have to fill that, within that capacity we have to fill the maximum number of value in the particular sock. So in that in the problem there is a 4 items of weight 4753 and value is 40, 42, 25 and 12. So first the capacity of sack is 10, so we have to fill within less than or equal to 10. We can get the maximum profit. So the last column we can calculate the V by W, that is a value divided by W. So for the item 1 the V by W is equal to 10, for item 2 it is 6, and item 3 is 5, and item 4 is 4. So this is useful for substituting in our calculating formula. So what is the formula we can use here means, here we are using that we already know that in the branch and bound it is a bounded problem. Either lower bound and upper bound can be used to solve the particular problem. It is a knapsack, so our objective is we have to get the maximum profit. So we can get using the upper bound, from each level we go to the leaf level. So the upper bound, the value can be calculated by the formula B plus capital W minus small w into VWI divided by Vi plus 1 divided by Wi plus 1. So the first step, start with the root node with W is equal to 0 and V is equal to 0. So based on this W0, V0 in the formula, we can get that upper bound value is equal to 100. So from that that is a 0, that the sack, now the sack is empty, so the upper bound value is 100. So now we go to the calculations. Now we fill the stack with the item 1 or item without item 1. So with item 1 we can calculate the upper bound, without item 1 again we have to calculate the upper bound. So the with item 1 means the value of item weight of item 1 is equal to 4 and the value is equal to 45. Substitute this in the upper bound formula, we can get the value is equal to 76. Without 1 means W is equal to 0 and V is equal to 0, but in the V I plus 1 divided by W I plus 1 for the item 2, so we can get the upper bound value is 60 for the without 1 calculations. So these two calculations we can to conclude that the upper bound, highest upper bound is with 1, so we can proceed that level. So again in from with 1 again we have to calculate with 2 and without 2, that is means we can fill with item 2 what is the upper value and without item 2 what is the value. So based on that, with 2 means the we can add the weight of item 1 with the item 2. So by adding these two, item 1 item 2 weight, we can get the weight is equal to 11, but it is not optimal solutions because our capacity of sack is 10, so we can drop that solution. So go to the next without 2 options. So and then without two options, W is equal to 4 and V is equal to 40, we can get the upper bound value is equal to 70. So again we go to the with 3 and without 3. Suppose that means item 3 is included or not included. So suppose the item 3 is included, our upper bound value is 69. Item 3 is not included means our value is 64. So based on 69 and 64, 69 is an upper bound value, so we can go to that that node. So after with the 3, again from that we can add, we can calculate the upper bound. So what is the when adding item 4, what is our value, and without adding item 4, what is our value. With adding item 4 means our calculation, with adding the item 4 we can get the maximum weight, that is, so we can drop that solution. So without 4 means we can get the item value of 65. So this is our final conclusions. So from the root to leaf, we have a solution, that is a subset. With we can have a subset, we can adding item 1 and 3, we can get the maximum profit of 65. With the weight of 9, we can get the maximum profit. So this is our solution to the given knapsack problem. This is a given problem using the branch and bound. So our solution, our final output will be from the set we can get the, from the value we can get the subset of 1, 3 with the maximum value, we can get the maximum profit. Thank you.